Hello, how you doing? Are you up on how neural networks rely on these math constructs referred to as tensors? Well, if not, then watch on with me for the next few minutes and I'll quickly get you up to speed. Okay, let's get started. To make sure everyone watching this video is aligned, let me quickly define tensors. Tensors are mathematical constructs that generalize scalars, vectors, and matrices to higher dimensions. They allow for the representation of multidimensional data, which is crucial in complex computations. In simple terms, a tensor is like a container that can hold data in multiple dimensions, making it versatile for various applications. So how do scalars relate to tensors? Well, scalars are the simplest form of tensors, representing a single number or a zero-dimensional tensor. How do vectors relate to tensors? Well, vectors are one-dimensional tensors, which can represent a list of numbers or a single row or column in a matrix. So how do matrices relate to tensors? Well, matrices are two-dimensional tensors consisting of rows and columns that can represent data in a grid-like structure. What happens when we go out one more dimension? Well, you get a 3D tensor. A three-dimensional tensor can be thought of as a stack of matrices, like pages in a book. Each page is a 2D matrix, and stacking multiple pages along a new axis forms a 3D tensor. Tensors can go into 4, 5, 6 dimensions and way beyond. Tensors in neural networks can become extremely large, depending on the model's size, number of parameters, etc. In large models, tensor dimensions can go into the thousands. Tensors are a core concept in linear algebra, extending vectors and matrices to higher dimensions. In fact, many tensor operations such as addition, multiplication, decomposition are generalizations of familiar linear algebra operations, making tensors essential for representing and manipulating multi-dimensional linear relationships. Okay, so now that we've covered tensors, let's go into the focus of this video, which is how tensors are used in neural networks. So how are tensors used in neural networks? Well, the first is tensors are used to represent data in neural networks. All neural network inputs, outputs, weights, and activations are stored as tensors. So here's an example of a tensor used as input to a neural network. Imagine a neural network implemented for color image classification. In this example, the input features will capture a 32 by 32 pixel color image with 3 channels. There's one channel for red, one for green, and one for blue. The input tensor produced is a 3-dimensional tensor of shape 32 by 32 by 3. Think of this as 3 32 by 32 matrices stacked like a book. Okay, so here's another example of how neural network model data is represented by tensors. Here, a tensor is used to capture the model weights. Imagine a simple model with 2 input features, 3 neurons in a hidden layer, and 1 output neuron. Let's call the 2 input features x1 and x2. Let's call the 3 neurons in the hidden layer h1, h2, and h3. With this, let's denote the weight matrix between the input layer and the hidden layer as W1. Each input connects to all neurons in the hidden layer, so W1 has 2 rows, one for each input, and 3 columns, one for each hidden neuron. The weights between the input layer and the hidden layer for this model can be stored in a 2-dimensional tensor of shape 2 by 3. Each column of this tensor corresponds to the weights that connect both inputs to one hidden layer neuron. So how else do neural networks use tensors? Well, in addition to being used in data representations, tensors are also used in neural network operations. In fact, the forward pass of a neural network is just a series of tensor operations. So what are some examples of some of these operations? So the first example operation is tensor multiplication. So let's denote an input tensor as x. This operation will combine the input tensor x with the weight tensor W1 to produce the layer's output tensor. This operation captures relationships between inputs and learned weights, forming the core computation of neural networks. Next, after this tensor multiplication, there is matrix addition. After multiplying the input tensor by the weight tensor, a bias tensor is added element-wise to shift the output. Let's note the bias tensor as B1. Each hidden neuron has its own bias, and this tensor addition operation with a bias helps the model better fit data by allowing activations to move away from the origin. Following this tensor addition, an activation function then operates on the tensor. This activation function takes the output tensor as input and applies a mathematical operation element-wise across all values in the tensor. In our example, let's note the hidden layer output tensor as h. Here we see h is equal to the activation function applied to z. If we assume that the function f is a ReLU activation function, it will set all the negative values in the tensor to 0. This transforms the tensor's outputs of one layer into a new tensor that introduces nonlinearity before passing it to the next layer. Okay, so now in addition to data representations and operations, there's a third area tensors are used in neural networks, and that is in model training. Backpropagation works by computing the derivatives of the loss with respect to each tensor, which was derived using weights, biases, and activations using the chain rule. These gradients, also stored as tensors, are then used to update the original weight and bias tensors during training. And finally, the last area I want to cover where neural networks use tensors is in scaling. The scaling of neural networks is possible because of tensors and linear algebra. We can train massive models today because tensors map naturally to linear algebra, enabling mathematical operations that GPUs and TPUs are designed to accelerate. So in summary, without tensors, neural networks as we know them today wouldn't be practical. In short, tensors are the universal language of neural networks, just like DNA is the universal language of biology. Okay, so let me know what you think of neural networks and tensors. Can you see how neural networks rely so heavily on tensors? Feel free to share your thoughts in the comments below. I want to hear what you think about this topic. Okay, thanks for watching. This video, along with all the other videos in this place, are listed in the YouTube description. I invite you to watch other videos on my channel. If you like the way I'm sharing this content, please consider subscribing. When you subscribe, this really helps my channel grow. One last thing, we all love technology, and we're all excited about all the innovation with the cloud and machine learning AI. But don't forget to carve out some time to live in the real world. Go outside, go swimming, go hiking, go climbing, go surfing, but get out and move your body. And if you do, let me know in the comments. I want to hear about this as well. And with that, have a great day. Thanks.